All right, so we're in section 3.4 now, talking about absolute extrema. So earlier in this section, we talked about local extrema, also sometimes called relative extrema. And we said that a value that a function attains, so like an output for a function, is considered a local extreme value or a local extremum if it is the smallest or largest value that the function takes on within some small open interval containing that x value that takes you there, whatever that is. Now, we've seen where a function can have multiple local minimum or local maximum values. And what we're after this time is what's called absolute extrema, which is the largest or smallest value that f takes on in its entire domain, as opposed to just within some small interval of our domain. So these are the formal definitions we're going to work with. F of c is an absolute maximum of f if f of c is greater than or equal to f of x for all x in the domain of f. So it's the largest value that f takes on in its entire domain. Absolute minimum is defined in a similar way, except f of c is less than or equal to f of x for all x in the domain. And if f of c is either a absolute maximum or absolute minimum, we call it an absolute extremum, singular, or absolute extrema would be plural. So here's an example where we're given a graph. It says the graph of this function has a domain of -3, 3, and we're asked to find the absolute extrema of f and determine where they occur. So notice from -3 to 3, that's from here to here. Oh, I just realized I wasn't showing you that. From -3 to 3, that's from here to here. So we are seeing the entire graph. There's no part of this graph that's off the screen, if you will. So really what I'm doing is I'm looking for the highest point and the lowest point. What is the absolute minimum? Abs min for short. Well, I'm looking for the lowest point on the graph, which is occurring in two different places, actually, one here and one here. These are the two lowest points. And I'm interested in the y coordinate of either of these points because that's what the output of the function is at that point, and that's what we're looking for, f of c. So the y coordinate of either of these points is 0. I can see that easily enough just from the graph. What would the absolute maximum be? Well, that's going to be the highest point on this graph, which I'm seeing right here at 3. That's my absolute maximum. Where do these occur? Well, the absolute minimum of 0 occurs in two places, at x equals -3 or +3, which I can just write as x equals plus or minus 3. And the absolute maximum occurs when x is equal to 0. That's the x coordinate of that point up there, so at x equals 0. Okay? That's one example. Let's take a look at another one. The graph of f of x shown below, right here, has a domain of the closed -5 to 6, closed on the left, open on the right, and then it's from 6 to infinity. So basically, it's the set of all real numbers that are greater than or equal to -5, except for 6. And we can see in the graph what's happening at 6. There's a vertical asymptote here. Notice also at -5, there is a hole in the graph and then a point up here. So I'm just mentioning that in case that's kind of difficult to see. So what is the absolute extrema, or what are the absolute extrema of this graph on the domain of this function? Well, if I'm looking for the lowest point, I can see that the graph kind of hits its lowest point right around here, but there's another hole in the graph there and then a point below that, and that is the lowest point that I can see anywhere. Now, granted, part of this function we can't see because part of it goes off screen. My window here only takes me to about x equals 13 and then a little bit past that. But the function is defined all the way to infinity once we get past that vertical asymptote of 6. However, it looks like the graph approaches the x-axis as a horizontal asymptote there. So I'm going to just operate under the assumption that this branch of our graph is always positive because it's approaching 0 from up above, but it never crosses it. So that means that this part of the graph that goes below the x-axis is going to be where I find my absolute minimum. And this point is the lowest point that I see. It's occurring at -8. So I have an absolute minimum of -8, and it's occurring at x equals 2. That's where I see that happening. Okay? What about an absolute maximum? Well, in this case, this graph has no absolute maximum because of this vertical asymptote here. I can see that as I approach from the left or from the right, to this vertical asymptote, so we're in x is equal to 6, both branches of my graph are going off to infinity. So there is no largest value that this graph attains because it keeps going higher and higher indefinitely. I would say that there is, I wrote that in a weird way, no absolute maximum. And that's fine. A graph is not required to have an absolute maximum or an absolute minimum. There are graphs that have neither. Okay? So a couple of examples just using a graph to find these absolute extrema. Now, even though that last example showed us that a graph does not have to have absolute extrema, there are certain conditions that a function might have that guarantee that both an absolute minimum and an absolute maximum will arise. And the guarantee comes from something that we call the extreme value theorem. So again, from the beginning of this section, we define an absolute extremum to be either an absolute maximum or an absolute minimum, which occurs over the entire domain of the function. But sometimes, in fact, oftentimes, we have reason to restrict the part of the domain that we're interested in to a closed interval. And so now we're going to adapt our definition of an absolute maximum or an absolute minimum in that we can be talking about the maximum or minimum value that a function takes on, but only over a closed interval within its domain. So if a function, this is the extreme value theorem, if a function is continuous on a closed interval AB, then it has to have an absolute maximum and an absolute minimum. It will always have both if it satisfies these two conditions. Again, it has to be continuous on a closed interval AB. Okay, this last example, if we look at the entire domain, or even if we look at some subset of the domain, maybe a closed interval like from 3 to 9, notice on that interval, the function is discontinuous. It has a vertical asymptote there. And also on that interval, there is no largest value. It doesn't have an absolute maximum. So the extreme value theorem would not have applied here because this function is not continuous, which is part of the conditions in the extreme value theorem. We need the function to be continuous. Okay? So with the extreme value theorem, if we can see that a function is continuous and we're asked for absolute extrema on some closed interval, we will always be able to find both types there. So let's take this example right here. I'm given this graph of f of x, and I want to find the absolute extrema on each of these two intervals I'm indicating here. So let's start with this first one, from -3 to 1. So from -3 to 1, we're talking about this interval right here. We're talking about from here to here, okay? So I'm not interested in what's going on outside of that interval. I only want to look inside this interval. Where do these absolute extreme values occur? Well, I can see a lowest point right here. So there is a lowest point, and then I also see a highest point, which in this interval appears to occur right here. Again, remember, the function does have larger values than this one, but not within the interval that I'm talking about. Within this interval from -3 to 1, that is the highest point. So I have an absolute minimum of -16. That's where the lowest point is as far as its y coordinate is concerned. This example is not asking me for where the extrema occurs, so it's enough for me to just write this. I have an absolute maximum at this point, which has a y value of 12. Okay. Now, I'm going to move on to this second example in a second, but I want to point something out that happened here. The absolute extreme values occurred either at a place where I had a horizontal tangent line or at one of the end points of the interval that I was looking at. So notice one of these absolute extrema occurred at x equals 1, and it gave me a maximum of 12, whereas the other one did not occur at an endpoint, but it did occur where I had a critical value. Remember, those horizontal tangents are where f prime is equal to 0. That makes it a critical value. So let's try this example and keep that in mind now that we've kind of identified that. -2 to 4. So now -2 is here, 4 is here. So I'm looking in this window. You can try to ignore this line right here, but I'm looking in this interval here. Okay, where's the lowest point and where is the highest point? Well, the lowest point, if I notice my graph starts from down low, goes up high, and then goes back down low again. So if I'm going to have a lowest point, it looks like it's going to happen at either of these end points here. I have this value at -16. It looks like this value also has a y-coordinate of -16. So that would have to be my absolute minimum, because none of the points within this interval from -2 to 4 have a smaller y value. My absolute minimum is -16. And it's actually fine. We've already seen this on the previous page, but it's fine that the absolute minimum is occurring in two different locations. We can have multiple x values that give us that same absolute minimum or maximum in another case. It's just that there can only be one minimum itself. We can't have a minimum of -16 here and -17 over here, because the -17 is automatically smaller than the -16 over here. But in this case, both of those had a y value of -16. Where is my absolute maximum? Well, that's the highest point within this interval, and that appears to occur right here at +16. So my absolute maximum occurs at +16. Only occurs in one place, but notice it did occur at a local maximum. It occurred at one of those critical values right here. So this is, we're seeing the same thing that we saw in the previous example. My absolute extrema are only occurring at endpoints of the closed interval that I'm looking at, or at the same location that a local extreme value is occurring, so at a critical value. This will always be true if a function has an absolute extremum in a closed interval. So this statement right here is making that kind of clear. If a function has an absolute extremum, it must occur at a critical value or at an endpoint. And to be clear, this is specifically talking about when we are looking for absolute extrema on a closed interval, because if not, then the endpoint part doesn't really make any sense. Okay, so with that in mind, we actually have a very straightforward and efficient way of finding absolute extrema of a function using those observations. It's what we call the closed interval method. So first thing that we do is we determine what the domain of f is, and then we check that the function is continuous on the closed interval that we're looking at. So if f is not continuous on that interval, we have to use a different method. And we'll see that at the end of this section. There's examples where we can't use the closed interval method for whichever condition is not being satisfied, and we have to approach it a different way. But if that's the case, we can move forward with this method. So there's two things that we need to check when we're using the closed interval method. We need to find all of the critical values of f first. And remember, those come in two different varieties: wherever your derivative is equal to 0, or wherever your derivative fails to exist, as long as the x value for which that happens is in the domain of f in the first place. Then we evaluate the function, the original function, not f prime, but we evaluate the original function f at all of the critical values you found in step 2. And then you also evaluate f at the endpoints of that interval. And what you're going to get, depending on how many critical values and how many, well, there's only ever 2 endpoints, but however many critical values you have, you're going to get a list of numbers out of that, a list of outputs of your function. Whatever the largest value that comes out of that function is, that's automatically your absolute maximum. Whatever your smallest value is, that's automatically your absolute minimum. because there are no other possibilities. By checking all of the critical values and the endpoints of your interval, you have checked all of the possible locations that an absolute extremum can occur, provided that your function, again, is continuous on that closed interval. So let's take a look at an example. Okay, we want to find the absolute extrema of the function f of x equals 1/4 x to the fourth minus 9/2 x squared plus 6 on this interval, -5 to 4. So before we can proceed with the closed interval method, we need to make sure that we're satisfying both of those conditions. So what is the domain of this function? Well, it's all real numbers. And not only that, because it's a polynomial, it's continuous on the set of all real numbers. So that means it's going to be automatically continuous on any interval I focus on. So we have the continuity thing in place, and then we're only looking at a closed interval. So we're good. We're good to move forward with the closed interval method. Okay, so we need to do a couple of things. First, find the critical values of this function. Start by taking its derivative, f of x, and that's going to be, this 4 will come down and multiply with the 1/4 to make a 1. I'm going to get an x cubed. Here, we're going to get minus 9x, and then the 6 becomes a 0. Remember, our goal here is to set this equal to 0 and then solve it. So I already know it's going to help me to factor. Let's pull the x out, giving me x squared minus 9. And then this factors, because it's a difference of squares, to x plus 3, x minus 3. If I set that equal to 0, I get x equals 0 or plus or minus 3. Those are the three solutions to this equation right here. Remember, for critical values, you also need to find values for which the derivative does not exist, but for which your function does exist, your original function. However, the derivative of a polynomial is always another polynomial, so the domain is going to be all real numbers again. There is no value of x for which this is undefined. So these are the three values I'm going to get as critical values. Now that I have those, I need to plug all three of these as well as my two endpoints for this interval into my function to get a list of values. Now, one thing to pay attention to before we do that, if any of my critical values were not in this closed interval here, then I wouldn't need to use it. So for example, if x equals 10 was one of my critical values, I wouldn't bother plugging that into the function. And the reason why is because 10 is not in this closed interval, and I'm only looking for the absolute extrema of this function on that closed interval. I'm only interested in x values that live in there. So I wouldn't bother with something like x equals 10. But all three of these numbers are in that interval, so I need to check all of them. So I'm going to find f of -3, f of 3, f of 0. That's my these are my three critical values, and then my endpoints as well, f of -5, f of 4. Okay. Now I'm going to just give you the answers to these. I'm not going to work it out because you know what to do. You're literally just plugging these numbers directly into this function, working it out. Use a calculator if you need to. It's fine. What do we get? Well, one thing worth noticing here is that everywhere I plug an x in, I'm raising it to an even power. So if I plug a 3 in, I'm going to get something. And if I plug a -3 in, I would get the same thing as when I plugged a 3 in, because in either case, raising either a 3 or a -3 to an even power is going to give me a positive version of the same number. So it turns out that when I plug in a plus or -3, I end up with -14.25. In both cases, -14.25. Okay. When I plug a 0 in, you should not need a calculator for that, because if you plug a 0 into any polynomial, the answer will always come out to, or the output always comes out to the constant term. Hopefully you can see why that's the case. I would get 6. Then if I plug a -5 in, I get 49.75. And when I plug a 4 in, I get -2. The absolute extrema are just the largest and smallest numbers that came out of this list. So the smallest number is -14.25. It occurred in two different places, but it's still the absolute minimum. So my absolute minimum is negative 14.25. My absolute maximum is the largest value that came out of this list, which was 49.75. Okay? Now again, I want to draw attention back to that extreme value theorem thing that we talked about, because that theorem may not have seemed terribly important, but it's actually one of the more important theorems and facts in calculus, because what it does is it takes this interval on which there are an infinite number of numbers. There's an infinite number of values in this interval that I could set x equal to. But what the extreme value theorem does is it says you don't need to check all infinity of those. That's impossible anyways. It tells me how to narrow that down to a small finite list of candidates for my absolute maximum or minimum values. I can only find absolute maximum or minimum values, assuming my function is continuous on that interval, at these critical values or at the endpoints. So that shortened the list of things I had to check. Okay? Let's try another example, one that's a little bit tougher. Same type of thing. I want to find the absolute extrema of this function, f of x equals x cubed over x squared minus 1, on the interval negative 1/2 to 1/2. As before, we want to check the domain of this function to make sure that we have the correct conditions in place in order to use the closed interval method at all. So, is this function continuous on this interval? Well, I know that it's not continuous everywhere. It's a rational function, and that the denominator has some zeros, that's going to be undefined. So if I were to look at my denominator, x squared minus 1, I know that that can't equal 0. I can solve this by factoring x plus 1, x minus 1 is not equal to 0. So that x is not equal to plus or minus 1. So this function is not defined at plus or minus 1. But we are safe. Even though this function is not continuous at those values, we're looking at an interval that does not contain either of those numbers. The interval from negative 1/2 to 1/2 is small, and it doesn't capture negative 1 or positive 1. So this function is continuous on this interval, even though it's not continuous at other points in its domain. So we are good to go ahead and move on with the closed interval method. Start by finding f prime of x. Now we have a quotient here, so I'm going to use the quotient rule. So the lower function times the derivative of my upper function. That's going to look like 3x squared times x squared minus 1 minus the top function times the derivative of the bottom function, so that's x cubed times, this would be a 2x down here, all over the lower function squared, x squared minus 1. Let's simplify this down a little bit. Oh, sorry, I meant to square that. Let's simplify this down, so I'm gonna do this. If I were to distribute that 3x squared in, I would get 3x to the 4th minus 3x squared. And then here, when I multiply this 2x to that x cubed, I'm going to get, it's a negative x cubed, negative 2x to the 4th over x squared minus 1 squared. Now this 3x to the 4th and that negative 2x to the 4th, I can combine those, and I'm going to get x to the 4th minus 3x squared all over x squared minus 1 squared. And remember, the goal is to end up setting this equal to 0 and solving. So I need to factor an x squared out of this, which leaves me with x squared minus 3 all over x squared minus 1 squared. Even though that number 3 right there is not an actual perfect square, I can still think of this as a difference of squares and factor it as x plus root 3 times x minus root 3, x squared minus 1 squared. So again, remember, we want to set that equal to 0 and solve it, because those are the only kind of critical values I'll get out of this function, since this function is defined everywhere in this interval and it's continuous there. So if I have a rational function and it's equal to 0, then I can only, all of the zeros of this function will come from whatever makes my denominator or my numerator equal to 0, but not my denominator. Those values would be x equals 0 from the x squared, or plus or minus root 3. Okay, because that's from these other two factors right here. However, I can ignore these because those numbers, even though they are critical values of the function, they don't live in the interval that we care about. We only want to use critical values that actually live in this interval. So I have a smaller list of numbers to check. When I plug these, I plug the critical value as well as the two endpoints of my interval into the function itself, the original function, to see what comes out of that. When I plug in a 0, I just get 0. I can see where that would happen. I have 0 in my numerator there. If I plug -1/2 in, it's some fairly simple arithmetic, but again, for the sake of not spending a bunch of time on arithmetic, I'm going to, oh, sorry, this one comes out positive. I'm just going to give you the answer. If you plug -1/2, you get a positive 1/6 out. If you plug in a positive 1/2, you get a negative 1/6 out. So of these, the negative 1/6 is the smallest, and then positive 1/6 is the largest. That tells me that my absolute minimum is negative 1/6, and my absolute maximum is positive 1/6. Okay? We just have one more page to these notes, but I'm going to do that in part 2.